Hi, welcome to Math with Townsend. This video is for calculus students who are studying optimization problems. In this video, we're going to take up a problem that involves speed, distance, and time as part of the calculations. Our goal will be to minimize time, and our math will involve the Pythagorean theorem. Let's have a look at the question. And certainly feel free to pause it if you want to read it carefully. But we have someone who's swimming across a lake and then running down beside the lake to try to get to a finish line. And for now, let's just emphasize the important thing is that our goal is to minimize the total time for the race. So we're minimizing the time. So let's just take a better look at what's actually happening in this question. So we have a person who is going to start at point A and is going to swim across the lake, get out of the lake, and then start running towards the finish line, which is here at C. And so the problem specifically states, determine point B that will minimize the total time. So what do I know about point B? Two event rays, point A on one shore to point B on the opposite parallel shore. So basically point B is the place where the swimmer gets out of the water on the other side and then starts swimming over. And then starts running over towards C. So we're going to swim to a point called B, and then we're going to run. And our job is to figure out where B should be on that opposite shore so that the time it takes is a minimum. So let's look at a couple things here. One is that there's a weird number 2. So this question involves speed, distance, time. So we're minimizing time. And information in the question is in terms of distance. So we have a distance, which is the lake width. We have a distance, which is sort of the running distance total is 10. So we have distances given in the question. And we have speeds given in the question. So the speed that we can swim, the speed that we can run. And what we're trying to minimize is time. So here in the corner, let me sort of emphasize that. I have written what I think of as the speed equation, which is speed is distance divided by time. I know that because when I go driving, I see signs that say 100 kilometers per hour. So distance, kilometers, over time, hour. So what I need to do is rearrange this so that I can write an equation for time. So the first thing is I'm going to multiply both sides by time. That gives me speed times time equals distance. And then finally, that's the equation I want. Now, you may know that better than I do. I'm not a physics student anymore. So I always have to develop it that time is equal to distance divided by speed. So that's going to be important. So now let's look at possible scenarios. So one scenario is that this person doesn't bother running at all. Maybe all they do is get into the lake here at point A and just swim directly to the finish line. So that's a possibility that we basically put point B at the same place as point C. So we tell this person, you know what, swim the whole way. So let's look at some numbers involved in this. Well, if this person's going to swim the whole way, we know that they're going to be traveling at 2 kilometers per hour the entire way because they're not running at all. And so we can calculate that distance that they're going to be running because what we have is a right-angled triangle. Ooh, pretend that's a right-angled triangle where we know that this is 10 and this is 4. So this is A, and then we put B and C right there. So they're going to go they're not going to go straight across. They're going to swim this way. And that distance can be calculated using the Pythagorean theorem. So a squared plus b squared and then square root the answer. So that distance, if you swim directly from A straight to C, is the square root of 116 or about 10.8 kilometers. And we can also, since we're here, calculate the time that would take. So the time it would take is distance divided by speed. So that would take about 5.4 hours. Oh, this is a longer race. So that's one possible answer, that the person should swim the entire way directly from A to C. It would take 5.4 hours. Okay, let's look at a different scenario. which is this time we're going to swim as little as possible. So if we're going to swim as little as possible, it means we're going to get in the water at A and we're going to go directly across the lake. So directly meaning perpendicular to the shore of the lake. And so we're going to swim as little as possible, which means we're going to run the entire 10 kilometers. So, and actually we're swimming the 4 kilometers. So we're literally going to swim 4 kilometers and then run 10 kilometers. And that would put this B point, which again is the point where you get out of the water and start running, right here at this directly across point. So that's also perhaps a possibility for the best, meaning minimal time. And we can use the numbers we have and calculate what time that would be. So we know that we are swimming at a speed of 2 kilometers per hour and the distance is 4 kilometers. So the time to swim in this scenario, I'm using a really thick pen here, hope that's okay, would be distance divided by time. So that would be 2 hours to swim that part. And then the time to run, we know that the run is 10 kilometers and it's 8 kilometers per hour. So 10 divided by 8 is 1.25, which means the total time would be 3.25 hours. Well, so far, that's the winner, right? That's nearly 2 hours better than the other time. So far, I'm saying this is the method. But of course, we need to find the absolute minimal time, which is where you're going to swim still at an angle. Like, so you're not swimming directly, but you're not swimming all the way there. You are going to swim part of the way, get out of the water at this in-between point B, and then run the rest of the way. That's the scenario that we need to do more math with because, of course, we don't know where point B is in this scenario. So one thing I'm going to do, though, is I'm going to put a new variable, well, not a variable, but I'm just going to define point D. D is going to be the point that's directly across the lake from A. And I'm just labeling it so I can call it something easier lately because we know that there's no point in swimming to the left of my picture of D. And it also helps me visualize that, oh, this is going to be a Pythagorean theorem situation. And I can clearly see the triangle that way. So D is going to be the point directly across the lake. And again, this is where we need to do all of our math. We need to start introducing variables and figuring out a way of calculating the time based on where B is, which means we need to introduce variables and stuff like that. So let me get a cleaner picture here. So again, I meant to put D here. Oops. And of course, there's that shouldn't be there. Ignore that. The 10 kilometers starts here. Okay, so we need to define a variable. So we know that we are eventually going to calculate the total time. That's what we're trying to minimize. So I'll just write that, minimize the total time. And the total time is going to be based on the time it takes to swim. So swim time plus run time. So let's talk about the run time first. The run time is going to be this distance. So I'm going to call, so that distance from B to C divided by 8. So the run time is going to be the distance B to C divided by 8. So again, distance divided by speed. Now the swim time is going to be the distance from A to B divided by 2. So, okay, great. Where's my variables going to go? Well, obviously the big math problem is that A to B is the hypotenuse of a right angle triangle, which means I'm going to have to use this side, which is 4 kilometers in length, and this side of that right angle triangle to calculate the length of AB. And so I need to know the length of this side, DB, because it's part of the triangle that lets me find AB. I also need to know this length because that's length BC. So that sort of suggests what I'm going to do about my variable. You can certainly let one of those distances be x and one be y, and use a constraint equation, but I'm just going to avoid that entirely just to make my life a little simpler. And I'm going to let one of these distances be x and the other one be 10 minus x, because together they have to add to 10. I mean, maybe I'll do that as a small constraint equation if you need it. But basically the question is, which one should I let be x? It actually doesn't matter, of course, math-wise, but it might matter in terms of the complexity of the problem. And because AB is going to be used in the Pythagorean theorem, or I'm using the Pythagorean theorem, then I want this distance that's part of that calculation to be as simple as possible. So I'm going to call that x. And that means if you want, you can temporarily call that y, knowing that x plus y has to be the whole distance, the whole 10-kilometer distance, and therefore y is 10 minus x. So I'm just going to call that 10 minus x. So that means that I have let x be the distance of the horizontal component of the swim. That's a nice answer in physics language. But in my diagram, I'm just going to call it distance dB, and that will be in kilometers. And that's okay because on my diagram, I've introduced point D as well. So then let's start thinking about what these equations might look like. So AB, I'm just going to use this cool tool for a second because I can. Yeah, look at that. Woo, one thing is neat in my video. Okay, so again, we called this distance x. We called this distance, well, it was 4. And this is the distance that we want to find. This was the swim distance. So we can calculate the swim distance as part of x because the swim distance is based on the Pythagorean theorem. So a squared plus b squared would be c squared, but I just want to square root it. So the swim distance is x squared plus 4 squared. So that would be square root of x squared plus 16, which gives me the swim time, which I'm trying to minimize as part of a bigger equation. I'm not minimizing it separately. Swim time would be distance divided by speed. So that is the time it's going to take me to swim that Pythagorean hypotenuse line. And now I need to figure out how long it's going to take me to run. So we're running 10 minus x kilometers. So for run time, the distance is 10 minus x and the speed is 8. So I have, in terms of x, all of my relevant times. So I can say that, again, my goal is to minimize time, and I can write a function for time. The total time is 10 minus x over 8 plus root x squared plus 16 over 2. Actually, I think I may have written it the other way, but doesn't matter which one goes first, I'm adding. And of course, normally before I then start to play around with that equation, normally I say, okay, well, what are my constraints? Well, there's not really any constraints because I haven't involved the letter y, other than momentarily at the beginning. What about restrictions on x? What is the smallest thing that x can be? And what is the largest thing that x can be? Well, this is actually fairly straightforward if you understand sort of the initial scenario, or the whole problem, is that wherever B is represents where we stop swimming and start running. So our scenario 1 was that we are going to stop swimming where the end is. So that would put point B right on top of point C, which would mean that the distance, sort of the sideways distance of my journey would actually be, how did I define x? 1 second. I want to make sure I let x be the distance from D to B. Okay, Simple. That's why you define it, in case you get confused like I just did. X is the distance from D to B. And so if you look at any of the diagrams where I have both D and B, like this one, the maximum distance would be 10, because you're not going to put B over here or over here, right? So the maximum distance between D and B is going to be the full 10 kilometers. Actually, that's the one we saw right here, where we swim as little as possible. And the minimum distance is, well, again, I'm not going to put B to the left visually of where I put point D. So the minimum distance between D and B is if they're actually at the same spot, which is 0. So my restrictions are that X has between 0 and 10. So if you're from my class and you've seen us do questions like this together, you know that this is always how I set up one of these equations. I think about the sort of swim all the way, or the all the way underwater, or whatever, like the true diagonal. And then I think about, what if I minimize that particular aspect and go directly across, and then we look for the in-between. And that's why these questions are more complicated math-wise, but the restrictions much easier. So where were we? We have our equation and we're minimizing the equation. So now there's a bunch of math to do, because we need to take the derivative, set it equal to 0, and solve. So what I've done, here we go, because my handwriting is messy in general anyway, and certainly on a tablet it's worse, is I have pre-typed it. I know. So let's look at this. So yes, I did reverse them. So this is the time it takes to swim, and this is the time it takes to run. And altogether, I have my total time. So first of all, I'm going to manipulate that algebraically before I take the derivative. So, for example, I'm going to separate the divide by 2 from a denominator position and just write 1 over 2 as a fraction. Much easier to deal with, to use derivatives if you see coefficients as fractions. And of course, I'm going to take the square root sign that you see, and I'm going to write it as exponent 1/2. And then what did I do with the blue? All I did was separate that into 2 different fractions. So I have 10 over 8, and then I have -1 over 8. And yes, that would reduce, but I'm about to take the derivative, and it's a constant term, so I don't really feel like I need to reduce it. Okay, so let's keep going. I think now I'm ready to take the derivative. So next step. So to take the derivative, we multiply the exponent times the coefficient out front, subtract 1 from the exponent, do not touch the inside, but then you have to take the derivative of the inside. So the derivative of x squared plus 16 is 2x. That's the derivative of this part. The derivative of 10 over 8 is 0, so it's not represented, you don't see it. And then the derivative of this is just -1 over 8. Okay, so we took the derivative, we make it equal to 0. So I've made it equal to 0. And what else have I done? Well, I've taken the parts. So this has a negative exponent, which means that it needs to be in the denominator. And you'll see I reverted the 1/2 to a square root. I also took the 4 that's in that coefficient fraction and put that in the denominator. And then, of course, the 1 times 2x are the parts that stay in the numerator. And I haven't touched this little guy at all. Okay, so we're almost ready to start solving. So what I've done now is I took, boom, boom. Kind of like teaching this way, just erasing some work. I know I'm right if I did it this way. So obviously I took this -1 over 8 and I added it to the other side. And then I also, well, this is multiplied by 2 and that's multiplied by 4. So I simplified those to be 1 and 2. So now I have a fraction equal to a fraction, so I cross multiplied. So I multiplied 1 times this. Boom. Ooh, interesting. Oh, I still have that tool turned on. And I multiplied x times 8. So boom. And then what would you do now? So I divided both sides by 2 because multiply by 2, why bother? I'm going to divide by 2. That's why you see 4x. So now I'm at the point where I need to just get rid of that square root sign. Oh, that's not working. I need to get rid of the square root sign, so I'm just going to square both sides. So square both sides. And we end up with this. X squared plus 16 equals 16x squared. Collect like terms, so obviously I took 1x squared, moved it over here. 16x squared minus 1x squared is 15x squared. Divide by 15. Take the square root. And of course, mathematically, the square root would mean plus or minus. But I know that I'm solving for x, and x represents a distance, so I'm not worried about the minus part of that. It's the square root of 16 over 15, which is 1.03. Whew. So now I can set up my testing table. You can tell I don't have that tool on anymore. So we're going to test 0, 1.03, and 10 in my distance formula. And of course, interestingly, if you look at the distance formula, sorry, the time formula, oh, not a distance formula, it's a time formula. If I let x equal 0, what I should get is exactly what I figured out in scenario 1. Because, oh no, scenario 2, sorry. Because scenario 2 is when D and B are in the same spot. So let's check that. Why not? Math is good. Let's check it. So one thing I'm going to do is I'm going to take a copy of my equation so that it's closer to me when I'm doing my testing right here. Okay, so if you sub 0 into this equation, you get, what do we get? So we get 0 plus 16 square rooted, so that's 4 over 2, plus 10 minus 0 is 10, plus 10 over 8. So I get 2 plus 1.25, which is 2.25. Sorry, 3.25, exactly what we had before. Good, I like when math works. Now let's do t equals 10. T equals 10 should give us that scenario 1 answer, scrolling, of 5.4 hours. Let's see. I mean, we know it's not the right answer, but let's just check our math. Scrolly. So if I sub 10, I get 116 divided by 2 plus 0. So the square root of 116 divided by 2. Oh, look at that. In fact, I remember typing those exact numbers in my calculator already. So this is technically 5.39 hours. Again, it's not recommended. It's a bit longer by more than 2 hours. But now the big one, let's test 1.03. So I'm going to sub 1.03 into the equation. And I'm going to do it in my calculator. I'm just making sure that you're comfortable with what is happening. That's a plus sign. Not sure if even I'm comfortable with that. Okay, so 103. Nope, 1.03 squared plus 16. Square root that. Divide by 2. So far I have 2.07 plus, and then 10 minus 1.03 divided by 8, I get 1.12, which gives me 3.19. So it's not that much better than just swimming straight across. I guess that's because compared to running, the swim speed is so slow. But it is a little better, you know. I mean, that's an extra 6 minutes or whatever. I mean, not even 6 minutes because it's decimal time. But what we've discovered is that the minimum time is 3.19 hours. 3.19 hours. when point B is 1.03 meters from point D. And you know, if you define point D, that's fine. You don't need to be all crazy descriptive, but you can. Okay, so I hope that was helpful. Keep doing math.